Okay, so this morning I want to go on with the presentation of the results of the Drude model. In particular, I would like to start from the second law of dynamics. That was one of the hypotheses that Drude used to describe the motion of the electrons within the solid. And what I would like to do is to try to include in this equation the contribution coming from the collisions, because in this case, the force, what is called force in the equation, is just the force due to external fields. So an electric field, a magnetic field, and electromagnetic waves, but there is not the explicit presence of the collisions in these equations. So it would be nice to have the collisions there, so that when you apply an external field, you both consider the contribution of the external field and the contribution of the internal microscopic mechanism that allows the system to, for instance, dissipate energy. So the idea for the calculation is the following: to start from the to start from this equation. So F is always the external force. And what we may try to do is to rewrite the first term where there is the derivative of the momentum of the electron in a slightly different way. So this is the, no, maybe too small. Yeah, it's my problem. I tend to write smaller and smaller, so I try to write larger. So the idea is to write to multiply both terms by the small amount of time dt. So we have dp of t is equal to f. And in principle, f may be also a time-dependent force. So I write t here, but in principle, that should be the time dependence, position dependence, whatever, times dt. Now, dp is the small variation of the electron momentum along time dt. So we may write dp as p at time t plus dt minus p at time t. And this is equal to f time dt. If we now take the momentum p at time t on the other side, on the right side, what we have is p, sorry. Okay, so the equation tells us that the momentum that you have at time t is due to two contributions. One contribution is momentum at time t. The other contribution is the force applied during this interval of time times dt. Now, you are able to see that p at time t plus dt is equal to that term if the electron from time t to time t plus dt does not suffer a collision, because otherwise p at time t plus dt does not depend on the force, because the collision erases any contribution coming from the force. So the idea is that this equation is valid only for the electrons that from time t to t plus dt do not suffer a collision. At this point, the idea is, what is the probability to suffer a collision from time t to time t plus dt? The probability as we saw yesterday, the probability is dt, the amount of time, divided by the relaxation time. If that is the probability to undergo a collision, then to evaluate the equation, the second equation of motion, we need to consider only the electrons that do not suffer a collision. So if that is the probability to undergo a collision, the probability to not undergo a collision is 1 minus dt divided by the relaxation time. So this is the probability that the electron will not undergo a collision. At this point, we may include this contribution into the equation. So P at time t plus dt is equal to F time t dt plus momentum time t multiplied by 1 minus dt divided by the relaxation time. So this, writing this is a way to say only the electrons that do not suffer a collision will follow the second law of dynamics, taking into consideration momentum and force at time equal to t. At this point, we may expand the two parentheses. So we have p times t plus dt is equal to f f dt times f dt squared divided by the relaxation time plus p minus momentum times dt divided by the relaxation time. All the terms in the equation represent momentum or force or a quantity times the small interval of time as the last term where we have p momentum times dt. There is just one term where we have force times dt squared. So we have the second power of the small interval of time. Due to the fact that dt is very small, so dt squared is expected to be smaller and smaller with respect to dt, we may neglect the term proportional to dt squared and stop the approximation to the first order. So what is generally done is to neglect the dt squared term. And at this point, what the procedure here is to go back to the initial point. So to try to reassemble the second law of dynamics. So to go back to the initial form that was that dp divided by dt is equal to f. So we may take back this p to the left side of the equation. So we have p times t plus dt minus p times t. On the other side, we have f times dt minus p divided by relaxation time times dt. So at this point, if we divide by this small interval of time dt, what we have is that we have this new equation. The equation is equal to the, let's say, second law of dynamics, apart from the fact that a new term here on the right has appeared, and this term is proportional to, is inversely proportional to the relaxation time, and is proportional to p, that is to the electron velocity. We have also a minus sign in front. So this is a sort of friction. As you see, if you remember the force that you have when you have a body that moves within, for instance, a fluid, you have the Stokes force that is due to the viscosity of the fluid, and the sign of that force is opposite to the sign of the speed, of the velocity. So that is a sort of friction. This means something is moving within a medium, and interaction with that medium produces a sort of friction, stopping force that tries to bring back the body to the equilibrium, to velocity equal to 0. So in this case, the macroscopic, let's say, from the point of view of the second law of dynamic contribution of the collisions is, let's say, to be non mi viene il termine frenare, is to try to reduce the speed of the electron as the electron is moving through the solid and goes on colliding with all the ions that, according to the Drude model, that are found within the system. So in this way, we have a single equation where we have both the external force and the contribution of the internal microscopic mechanisms that rule the motion of the electron. So this new version of the second law of dynamics will be used from now on to evaluate all the properties of the details of the motion of the electron within the solid. The first, let's say, topic that where I would like to use this equation is one topic concerning the application of a DC field. So something that resembles what we used yesterday. So yesterday the discussion was about conductivity. Here today, again, we start with conductivity, so static field, a field that does not depend on time. And in this case, the idea is to see how the metal, according to the Drude model, behaves when we apply both an electric field and a magnetic field. So the idea is, with respect to yesterday, let's include an additional magnetic field to the system, along with the electric field that was applied also yesterday. And what is the idea behind the application of two fields, the electric one and the magnetic one? Both ideas are related to experimental findings. So one experimental finding was that if you take your piece of metal and you connect the piece of metal to a wire and you apply an electric field along the horizontal direction. So let's suppose that the horizontal direction is the x direction. Then if we take three orthogonal axes, we have x horizontal, y vertical in this sheet, and z that is orthogonal to the sheet. So I just write here we have white and z is going out of the blackboard. And if we just apply the electric field, we see that what we saw yesterday is going to happen. Now, they also try to measure the resistivity of the system when an external magnetic field is applied and is orthogonal to the plane of the material. Experimentally, they found that if you apply a magnetic field while you're measuring resistivity, resistivity increases. So what they found was that if you plot here B modulus on the horizontal axis, and if you plot on the vertical axis the resistivity as a function of B, then you start from the resistivity value that you observe with zero field, and then you see something like this. So resistivity increases. The increase depends on the metal. So the percentage of variation changes from metal to metal, but in general, you have an increase of resistivity. So the idea was, behind the experiment was the following. The question was, is Drude model able to predict the fact that the resistivity of the system changes as we apply a magnetic field? So this was the first question. The second question was related to the a sort of validation of the Drude model, because the Drude model was formulated slightly after that Thomson discovered the electron. So the general idea was that the electron was the sort of the light particle within the solid. So they initially thought that if you apply a voltage and you see a flow of current, then that flow of current should be due to electrons, so negative particles. But this was the hypothesis, and they tried to validate the hypothesis to check whether it's actually true that the electrons are making current flow within the metal. So how to answer to these questions, or how to validate the model? The idea can be observed if we look at this diagram here. So if you have, let's suppose that the electrons are the particles that carry the current. So if we apply an external, here I do not write, okay, it's better to write the vector. So if I apply an electric field in the horizontal direction, then I see that if the electrons are the particles that carry the current, yesterday we saw that the density current is can be written in that way. So if the electric field is applied to the right, then the electrons move to the left, and as the electron moves to the left, the density current is applied to the right because you have the minus sign. So in that case, J, I write Jx because it's J in the direction of the field. So Jx is expected to be in that direction. Then what happens to the electrons due to the presence of the magnetic field? Due to the magnetic field, we have the Lorentz force on the electrons. So the Lorentz force is in general, the general expression is that. So the velocity of the electron is with respect to that diagram to the left. B is orthogonal. So in principle, the force should be upward, but there is the minus sign to the electronic charge, so the force is downward. This means that if the electron is the particle that carries the current, the force on the electron is downward. So what happens is that the right part of the slab charges in a negative way because the electrons are forced to go to the right. Due to the fact that the electrons are forced to go to the right, the left part of the metal charges in a positive way because you remove positive charges, you move negative charges from the left to the right. So here you have a positive charge on the other side. What happens due to the fact that you produce these two charge distributions? Due to the charge distribution, you have an electric field that is downward. So in this case, we have EY that is downward. And what is the effect of EY? If EY is downward, this means that the electrons are forced to go upward. So this field tries to, at some point, obtain the equilibrium, because if we just leave there the Lorentz force will continue to send electrons to the right. But this produces a charge density on both sides of the slab that is continuously increasing. So to stop this phenomenon and to try to bring back the slab to the equilibrium, this EY electric field sets in, and the field tries to oppose to the Lorentz force. So in this way, we have a charge density that is negative on the right, positive on the left, but this charge density at some point reaches an equilibrium. And the equilibrium is between Lorentz force and the effect of EY. So if the flow of current is due to the electrons, what we obtain is that the right part of the slab is negatively charged and the left part is positively charged. Now let's see what happens if the flow of current is not due to electron, but is due to positive charges. So what happens if the current is due to positive charges? So same diagram, always an electric field that is horizontal, Ex. In this case, if the current is due to positive charges, Jx is always to the right, because we have that the electric field forces the positive charges to go in the same direction of the field. So Jx is always like this. At this point, again, we apply the Lorentz force. Jx is to the right, the B is upward, not upward, out of this plane, so the force is downward. So in that case, the positive charges are forced to reach the right side of the slab. If the positive charges go down, then the negative charges are found on the opposite side. So the opposite side charges negatively. So in this case, if the charge carriers are negative, you expect that the right side is negative, left side is positive. If the charges that carry the current are positive, then you expect right side positive, left side negative. So the orientation, and in this case, EY is upward. So what changes depending on the sign of the charge is the direction of EY, or the sign of the voltage across the slab. In one case is negative, in the other case is positive, depending on the orientation you choose for the measurement. So the idea is, with this experiment, with the whole experiment, it is possible to evaluate the sign of the charge carriers. So thanks to the fact that this experiment distinguishes if the current is due to negative particles, electrons, or positive particles, then it is possible to validate the approach of Drude. So if in this case the voltage, the EY is negative with respect to the orientation of the y-axis that I used in this diagram, then the electron picture is fine. If EY is positive with respect to the orientation of the y-axis, then the hypothesis is wrong, and we have to go back to the idea that the electrons not go back. But we have to change the model again, because the positive charges have to be considered. So now the idea is try to answer to these two questions. First question is, does the resistivity changes according to V? Second question is, what is the sign of the voltage, or what is the orientation of EY? And according to those two answers, we may decide whether both are in favor of the experimental result or not. So because experimentally they found that the voltage was like the first picture. So actually experiment told us that the charge carriers are actually electrons. So the experiment validated the picture. So the idea was to confirm the fact that this was also the answer from the hypothesis of the Drude model. So I just I don't know how to cancel parts of this picture, because I started to use this just this morning. So I now make another diagram. Yeah. So what we do now is to apply the second law of dynamics that includes the contribution of the collisions to this picture. Okay, we have expectations concerning the sign of EY. So we expect that if everything is correct and the electrons are actually carrying the current, then EY will be directed in the negative direction of the y-axis. But so what I will do now is to write this equation, the two components of this equation, because we expect to, let's say, there is no force in this z direction, so I do not write the z component of the second law of dynamics. And what I will do is just to write down into the equation the different contributions. I will not introduce the information concerning the direction. So I will not, for instance, write EY with a negative sign because I expect that EY will be negative. I just write EY and I expect that the equation tells me that EY is negative. So I do not fix from the beginning the sign of the parameters. I expect to obtain those signs directly from the equation. So from the x direction, we have another thing. At some point, okay, I write the equation and I make the comment. For sure, as soon as you apply the electric field, there will be a slight amount of time during which the P is not a constant, because at the beginning you have the starting of the flow of current, so the system will not be in equilibrium. There will be again an interval of time where the P and the density current change with time, but at some point we will have a steady flow of current. So let's say the idea here is not to study this initial point where the current starts to flow, but to observe the equilibrium status where when the current is fixed, constant, does not depend on time. Due to the fact as as the density current is proportional to the speed, and the speed is related to P, at the equilibrium we expect that V is constant, so it does not depend on time. Due to that, also the derivative of P is expected to be equal to 0. So if we're supposed to solve this equation at the equilibrium, this will be equal to 0, and this will be equal to 0, because we're supposed to stay at the equilibrium. So set that equal to 0 just means that the current is there and is not changing, not the current is equal to 0. So Fx F is the Lorentz force, where we have both the contribution of the electric field and of the magnetic field. So in this case, so to make the vector, I write that down there just to not have the matrix within the calculation. So to evaluate the x component, we see that the x component is just, sorry, not the y, b. Okay, minus px. Due to the fact that, again, I do not expect the current changing with time, I remove the t dependence from p. And this, just to have just p, only p in the equations, is equal to minus c ex plus px divided by m times B minus Px divided by the relaxation time. Then concerning the y component, I have minus C, then Ey. The y component is minus. In this case, I just write, sorry, here I wrote x, but actually is a y. So please change the label of this velocity because it is y. Then here I have px divided by m times b minus py divided by t. And this is expected to be equal to 0. Then I just open the parentheses. In the second term, the term where we have b, we have a common feature in the two equations, that is EB divided by m. Have you already found this ratio, EB divided by m? Do you know the meaning of that? No? If you take if you take an electron with a constant speed and you send that electron in a region where you have a uniform magnetic field, the electron starts to make circular orbits. And if you write down what is the force acting on the electron, that is the Lorentz force, and you say that the Lorentz force, in the case of the circular motion, is the centripetal force that brings the electron on the circular orbit, you find that EB divided by m is the frequency of the electron along this orbit. So EB divided by m is also called the cyclotron frequency, to resemble the fact that is in value that corresponds to the again frequency of the orbital motion of the electron when you apply an external field equal to B. So due to that, in these two equations, the term EB divided by m can be written as omega c. So we have continue. I'm sorry, I don't know why I write x in place of y. And this is x. Okay, now for both questions, in particular for the first one, so how the resistivity changes depending on the external field, it is useful to introduce in these equations the density current in place of P. So due to the definition of the density current, J is minus NE times P divided by M. See?
Could you please scroll down because I don't see the low.
Okay.
The lowest thing okay, thank you.
Ooh, sorry, I didn't notice that the last equation is right at the border of the blackboard. So now I just rewrite this equation here. Okay, sorry for that. Now I'll check. And this was the last.
Thank you.
The last equation. Now I rewrite everything taking into consideration the density current. So I multiply so I multiply everything by n e divided by m. And this okay. So this is Jx. This is Jy. Then so so the second term in the first equation is Jy. Then we have plus Jx divided by the relaxation time, that is equal to 0. And in the second equation, we have minus n e squared divided by m minus omega c jx. And then we have plus jy divided by t. The relaxation time is equal to 0. Then n e squared divided by m resembles the conductivity. We just miss one relaxation time to have the actual shape of the conductivity. So I multiply everything by the relaxation time. So here, so if I multiply by the relaxation time, I have in the first equation minus sigma ax plus omega c jy times relaxation time plus jx is equal to 0. And in the second equation, I have minus sigma ey, then I have minus relaxation time omega c jx plus jy is equal to 0. If you remember the diagram that I made at the beginning, where there was the slab and Jx was on the horizontal direction, what is Jy? Jy is the flow of current that flows along the y direction. At the beginning, when you switch on the magnetic field, you will have a flow of electrons going to the right side of the slab. But when the EY field sets in and you reach the equilibrium, what you expect that at some point, Jy will be equal to 0 because there will be no more a flow of current orthogonal to the direction of Jx. So at the equilibrium, we expect that Jy is equal to 0. So at the equilibrium, that means when Ey and B are where the intensity of Ey is such that the effect of the Lorentz force is counterbalanced by Ey, we have Jy equal to 0. Jy is equal to 0, we can remove that from the first and the second equation. And if you look at the first equation, we have just Jx equal to conductivity times Cx. And this is just the equation that we obtained yesterday. So the same equation that was found when no magnetic field was applied to the system. So this is the answer to the first question. So the answer is no, the resistivity or the conductivity of the Drude metal does not change in case you apply an external magnetic field. So this theory fails when the theory tries to explain why a magnetic field may somehow affect the conductivity of a system. The answer to this question will be yes, when we will use more sophisticated models to describe the motion of the electron. So at the end, we will be able to predict the fact that the resistivity of the system changes according to the magnetic field. But to say yes to that question, we need a more detailed structure of the electronic orbits within the solid. So at this point, it's not possible to predict a field dependence of the resistivity. Let's see what happens concerning the second question. So the sign of Ey. In the second equation, we have that Ey is equal to minus Jx times relaxation time omega c divided by sigma. Now, apart from the contribution of omega c and sigma is positive, omega c is positive, Jx is positive. So at this point, Ey is negative. So that is fine. So that confirms the fact that actually, as observed by the experiment, the orientation of the electric field that sets in the vertical direction is negative. Now, what was the next step? The next step is how, let's say, what are the elements that I think contribute to the modulus of Ey? So what is the expectation concerning Ey? Ey is expected to be related to B, because B is the Lorentz force that deviates the electrons and produces the polarization, let's say, of the slab. So one expects that Ey is related to B. Another thing is the contribution of Jx, that is the horizontal current. The horizontal current is proportional to the number of electrons with the given speed that move in the horizontal direction. Since the Lorentz force applies to the electrons that move with the given velocity, then what you expect that the higher the flux of current, the larger will be the number of electrons that will propagate in a given direction. So the larger will be the number of electrons that will be deviated as the magnetic field forces the electrons to move to the right side of the slab. So what they expected is that Ey was both proportional to B and proportional to Jx. So they defined a coefficient that is called Hall coefficient, and the Hall coefficient is called RH, is Ey divided by B modulus and divided by Jx, because they expected that, again, the field, the electric field that develops due to the Lorentz force is proportional both to the Lorentz force and to the intensity of the current moving in the x direction. So if we now try to expand, Yeah.
Can I- In here, the JX, according to the root model, we said by applying the magnetic field or resistance conductivity will change, but we find that in X direction it's not true. It didn't convince. It didn't. It's not correct. The root model, the J direction.
Could you please repeat, because I was not able to hear clearly?
Okay, we said okay in the X direction, the JX, it's the because according the we know that if we apply the magnetic field, it should to be change the conductivity.
Yeah, in principle, yes.
Yeah, but
Experimentally.
yes, but in X direction when we solve it, we say we saw that didn't solve it. It means the root model it doesn't work for the Hall effect, no?
No. That means that the root model does not work for the magnetoresistance. This means that the fact that the resistivity changes according to the magnetic field. In that case, that fails. We have not still checked the validity of the model concerning the Hall effect. It was let's say, the X equation. Thanks for the question, because I didn't point out this at the beginning. The X equation is related to magnetoresistance. So the X equation, this equation is is related to the question about the magnetoresistance. So does resistivity changes according to B? The second equation is the equation concerning Hall effect.
You mean the Y?
Yes, please.
The Y direction. You mean the Hall effect? I didn't understand.
Yeah. The why, because the electric field that sets in when you apply the magnetic field is only in the Y direction. And so the equation concerning the Y direction is the equation about the Hall effect.
Okay, thank you.
Yeah, so we have relaxation time. Then omega C is EB divided by, yeah, please.
No, sorry, by mistake. Nothing, sorry, continue.
And then the conductivity is electronic density E squared relaxation time divided by the electronic mass. At this point, we may simplify relaxation time, simplify the electronic mass, simplify one electronic charge, and what we have is this is equal to minus Jx times B divided by Ne, electronic density times electronic charge. Due to that, the Hall coefficient is equal to EY, that is minus Jx times B divided by Na, divided by B and divided by Jx. At this point, Jx and B can be simplified, and what we are left with is minus 1 divided by Ne. So Jx and B are removed from the equation, and just the electronic density and the electronic charge are left in the Hall coefficient. And this is quite important for different kind of motivations. One motivation is the first motivation is here you have no relaxation time. So whatever the collision mechanism, whatever the value of the relaxation time, that is not here. So if you measure the Hall coefficient, you have a quantity that does not depend on the relaxation time. And it's important because at the moment, the relaxation time has not a strong physical background. There's not a strong physical motivation behind the relaxation, the origin, the physical origin of the collisions. So due to the fact that we have a question mark on who is producing collisions, we have also a question mark on tau. So tau is needed, but what is the origin of tau? At the moment, we do not know. And the fact that here you have not tau is important because that is a quantity that does not depend on the details of the scattering mechanism. And another important thing is that here you have just N, the electronic density. Yesterday we saw that to fix N, you have to choose Z, and Z is your choice. So Z is chosen from the beginning according to your expectations concerning the number of electrons that are shared between the atoms to produce the metallic bonding. In this case, N can be measured. So you have a direct estimation of the electronic density of your system. So the Hall effect is also important for that. And you have the minus sign in front, so an indication of the fact that the charge that is moving due to the application of the external field is negative. And this was fine. Let's say at this point, if you see that coefficient, then you go directly to the lab. You take everything you have metallic in your lab and start to measure the Hall effect. And if you measure that on alkali metals, then the agreement is fine. So you find something that is very close to the value that is predicted by the theory. For instance, if you take alkali metals, you expect Z to be equal to 1, so you are able to predict the electronic density. And if you compare the Hall coefficient with the number that you calculate, then you find that they are pretty close. So that is fine for alkali. And also for alkaline earth metals, that is the second column of the periodic table. So also in that case, the agreement is fine. Then another kind of metal that was used for this kind of experiment was a metal belonging to the noble metal column. And later on, we will see why noble metals are important. And also for noble metals, let's say the agreement was fine. But if you take any other metal, then the agreement failed. In particular, for some metals, the Hall coefficient was positive. So, and to add more indications, for other metals, the Hall coefficient changed according to B. So, and the Drude model predicts just that the Hall coefficient is a coefficient, so does not depend on B, and in principle should be always negative. So the fact that the agreement is fine for some groups of metals and not fine for other groups of metals means that something good is found within the model, because you have agreement for some groups of metals, but maybe we are missing something, because in this case we are not able to predict the dependence of RH on the magnetic field, nor we are able to predict the fact that the coefficient may change sign, because apart from the Drude model, more or less 13 years later than the Drude model was presented, Rutherford performed the experiment concerning that allowed to establish that the positive charges were located in the nucleus, and thanks to the Bragg experiment, we know that the nuclei are regularly displaced in space. So they are displaced depending on a lattice, on the regularity of the lattice. So at this point, it's clear that due to the fact that the nucleus is heavier and heavier with respect to the electron, and is in particular located in a fixed position, then the nucleus is not able to carry any current. So the particle that brings the current is the electron. There's not the opportunity to is the Hall coefficient changes sign. So now this doesn't mean that one has not to sleep during the night because he thinks, oh my God, why the Hall coefficient changes sign? But please keep in mind those questions, because every time we will switch to another model, another way, a new approximation to the description of the properties of the electrons in the solid, we will take those questions in mind to see whether with the new approximations or the introduction of quantum mechanics, it will be possible to answer or to, how can I say, predict what is experimentally observed. So please keep in mind those questions, and we'll try to answer to those questions later on during the lessons. Okay, and yeah, it's 10 o'clock, so I think I may stop here, make a break, and then we may go on with the second part of the lesson. And I just two questions. I first asked to the guys here, and then I asked to those who are connected. Siete riusciti a vedere? È andata abbastanza bene così? Ok? And for those who are connected, was fine enough the opportunity to have this window shared? Can you see clearly? Do I have to write down more large characters?
No, it's fine. It's visible.
It's fine, thank you.
It's
Okay.
visible.
Okay, so now we make a 10-15 minutes break, and then I go on with the second part of the lesson.
Okay, thank you.